Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will talk in more detail about the phase plane analysis and include specific results like the Poincare-Bendixson theorem as well as the concept of limit cycles. So let's start without waiting. So we are going to start our phase plane analysis x1. So we are talking in 2D. So x1, x2, where the qualitative form, we are going to just talk about the qualitative form of solutions, and we consider the two forms of we consider the most general form of 2D system. X1 dot is equal to F1 x1 x2 t, and x2 dot is F2 x1 x2 t, and we have that F1 and F2, we will assume that to simplify our life, we are going to assume that F1 and F2 they are independent of the variable time. So they are they have no explicit time dependence, right? Explicit time dependence. So this is an autonomous system. Okay, autonomous system. And what we have is, so we can write the most general form. X dot is f of x bar, and we are writing it in the vector form, where x is x1 x2 and f is f1 f2, right? So what we have is that the variables x1 and x2 are represented by we are talking in 2D. So let us now quickly introduce some terms. So the first terminology is that of phase plane. So what do we mean by phase plane? So we say that when the variables x1, x2 can be represented by a point, in the x1 x2 plane. Variables can be represented by a point in the x1 x2 plane, and the locus, so this is the phase plane. We call the set of all these points as the phase plane, right? And the locus of all such points is the phase path. Locus of all such points is the phase path, and the set of all phase paths is the phase diagram. Okay, so when phase paths can also be, sometimes we refer phase paths as phase trajectories. So then let us quickly look at an example to start our understanding. What we have is, the problem says we are given an autonomous system. x1 dot is x2 minus 1 and x2 dot is minus x1 plus x2, and we have dx 2 by dx1 is x2 dot by x1 dot is minus x1 plus 2 by x2 minus 1. Okay, so dx2 by dx1 is this, and we have that x1 dot is x2 minus 1. Well, it's all given, so I have used the implicit rule here, and we can integrate this equation right away, and we see that we are going to get the following equation: x2 minus 1 square plus x1 minus 2 square is equal to c. Right, we can use it as the constant as c square. Now, of course, we all know that this is an equation of a circle with center at 2 comma 1 and radius equal to given by the constant c. And so what if we go deeper into phase plane analysis? We expect that we know that the center being the equilibrium point, and then the nature of the equilibrium point is that it's neutrally stable, it's a center, right? So I'm not going to go into those sort of details, but we'll just touch upon the aspects of phase plane analysis which will be utilized by us in our classical mechanics later on. So I end this problem by just showing you the phase diagram here, that the phase diagrams are circle, they are concentric circles, right? And with a common center, and the center being the equilibrium point, and the point is neutrally stable. Okay, so then I quickly state a theorem here. The theorem basically tells us or gives us a criteria as to when the point the theorem basically gives a criteria about the existence of the solution and how it relates to having a unique phase path in the phase diagram, right? So the theorem, this is only valid for autonomous system, and it says that each point of the phase space of an autonomous system has exactly one phase path passing through it, right? So each point on the phase space of an autonomous system has exactly one phase path passing through it, and the proof can directly come from the math, that the system, we look at the system of ODEs which represents the phase space. This is f of x bar, and this will have a unique solution. We directly state the condition: we have a unique solution provided f is Lipschitz continuous, and all these details people can refer to some standard real analysis textbook. The moment we have Lipschitz continuity, we expect a unique solution at any given time point, and the unique solution implies that the phase paths can never intersect at different times, right? So at a given time t, the solution is unique. Okay, or the trajectories never, another way to say it is they never intersect. The phase path never intersect. Okay. So then let us look at some specific cases of phase plane analysis, namely the case of simple harmonic motion. We have that linear, so phase plane dynamics. phase plane dynamics, and we see that the case of a linear oscillator, we have x double dot plus 2k x dot plus omega square x is f of t, and this is our linear oscillator here, and let us call this equation with star. And now I want to study this problem in the phase plane, through phase plane analysis. So first step in studying this problem is to convert this second order OD into system of two first order ODs. So we introduce a new variable x dot equal to v. And now my original equation star can be rewritten as v dot is equal to f of t minus 2kv minus omega square x, right? Okay, so then we have that f of t is 0. So let us assume the idea is we are assuming an autonomous system. So for autonomous system, we assume that the forcing is 0 because there is no explicit time function on the right hand side. And then we can see that in this case, we will have three different cases of solution or the phase diagram. So case 1 is when k is 0. In that case, we expect the solution, the equilibrium to be 0, 0, and the equilibrium is a center, right? So we expect the the equilibrium point to be neutrally stable. For k less than omega square, we expect an inward spiral. And we see that the solution is damped. And finally, it is damped, but it is underdamped. The word also is subcritically damped. And the second is for k greater than omega square, we have that this is overdamped, which means that the solution quickly converges to 0 faster. So this is an overdamped system with a supercritically damped setup. Supercritically damped. Okay. So then let us look at some more examples. We have one more example of, again, a nonlinear oscillator, which people in nonlinear dynamics will quickly recognize as the Duffing oscillator. So undriven Duffing equation, and we have x double dot plus omega square x plus lambda x cube is 0, and we have lambda is less than 0, and we have that the system of equations, system of first order equations gives us x dot is equal to v and v dot is equal to minus omega square x minus lambda x cube, right? So then we see that we can again, we have broken down the system into system of two first order differential equations by introducing the variable v, and from here we can find out a common equation dv dx is equal to minus omega square x plus lambda x cube by v, and this is also equal to, if we integrate this equation, we see that this is v square is c minus omega x whole square minus lambda by 2 to the power x to the power 4. Okay. So, so that is what we have, and the equilibrium points are, of course, we can see one equilibrium point is 0, 0, x equal to 0, v equal to 0, and the other equilibrium points, remember this is a cubic equation on the right hand side, so the other two equilibrium points are omega by square root of capital lambda comma 0, right? So there are two more values here. And then again, we are not going to do phase plane stability analysis of the phase equilibrium points, but I am going to quickly state the results. We can check that 0, 0 is a center, and we can check that these 2 points equilibrium are saddle nodes, are saddle points. And if we complete the phase diagram, we see that the center, we expect the center to have, the trajectories close to the center being circle, and the trajectories which are closer to these values minus omega by omega comma 0 and the plus value, these are right. So these are my saddle points here, and we see that this is going to be my phase diagram. My saddle points are these following, so we expect that the arrows will be drawn in this fashion in the saddle point, and that is how it is, right? So then what we have is, outside the region, what are we going to get? So we have essentially in this phase diagram, we can see two regions. Inside this, if we draw these dotted lines, we see that inside these dotted lines, these two lines, let me call this as L1 and this second line as L2. Within these two dotted, inside the region bounded by these two dotted lines, all the phase trajectories, they are bounded, right, or they are closed. And the trajectories outside these two lines L1, L2, they are not closed. So these two trajectories have a special name, L1, L2. They have a special name. They are also known as separatrices. Separatrices, and separatrices separate out your region having closed curves and region which are open curves or not closed, right? So closed loops and so on. Okay. So so what have we got here is, let us look at, so these are some starting examples. Now let us directly go to the result that is very important for our further analysis, namely the Poincare-Bendixson theorem. So let me directly state the result. Poincare-Bendixson theorem. Okay. So what we have is, suppose a phase path of a 2D autonomous system. Suppose a phase path of a 2D autonomous system lies in a bounded domain of the phase plane. The phase plane of a 2D autonomous system lies in a bounded domain of a phase plane for t equal to 0. For t greater than 0, then a phase path, this theorem states the phase path either closes onto itself, we call, in such an instance, we call this as a loop, or of course as this equilibrium point being a center. And the other option is it could either terminate at an equilibrium point, which means that the phase path eventually asymptotes towards an equilibrium point, especially when the equilibrium point is stable equilibrium. Or the third case is the phase path tends towards a limit cycle, or a degenerate limit cycle. Okay, so I call limit cycle as LC. So let me draw all these four cases. So essentially there are four cases. The last case has two sub cases, either a limit cycle or a degenerate limit cycle. So the first case is when the loop closes onto itself. So we have a center, right? And we see that this center is the following, and this is the case when the solution is bounded, right? The trajectories are bounded and closed, of course. And the second case is terminates at an equilibrium point. So we will have the case 2, where we see that this is the case of a phase path tending towards an equilibrium point. And then we see that the third case is that of a limit cycle, where we will have a limit cycle. So all the trajectories inside will tend towards the limit cycle, and all the trajectories outside will also tend towards a limit cycle in the other direction, right? So this is the case 3. I would say case 3A. And finally, we could also have a case of degenerate limit cycle, where you could have a degenerate loop, which essentially consists of I would say it's not a loop. Essentially, this is an equilibrium point. The loop contains an equilibrium point, and the rest of the trajectories are all closed inside or outside, right? So that is what we have. So this is a strange case. The last one, case 3B, is a strange case of a limit cycle, where the limit cycle contains an equilibrium point. So the degenerate case. Okay, so most of the effort, especially the idea of using Poincare-Bendixson theorem, is typically to figure out whether the system has a limit cycle or not, right? And this whole idea works only in 2 dimensions. In 3 dimensions, there are counter examples. So let us look at an example. So we have the case. Let us look at this particular case here. So proving the existence of limit cycle. So let us look at an autonomous system. So x dot is x minus y minus x square plus y square by times x, and y dot is x plus y minus x square plus y square times y, and this has a limit cycle. We have to show that this system has a limit cycle. Okay, so the fact that this particular problem has these terms x square plus y square suggests us that we could possibly use polar coordinates, right? So if we change my x with variable r cos theta and my y with variable r sin theta, we see that my new variables are r dot is r times 1 minus r square, and theta dot is 1, right? And we see that in this scenario, we will have to figure out that there is a limit cycle. So now we have a much simpler system. now, so the idea is we have to show that this has a limit cycle. So to show that there is a limit cycle in this system, we have to figure out a region, a special region where the limit cycle might exist, right? So my claim is I am going to take consider the concentric circle. Consider the concentric circular region, right? Consider the concentric circular region, and we see that we are not now going to take such that this lower radius, the radius of the inside circle is r1, and r1 is less than 1, and r2 is greater than 1. So this is my concentric circular region where which contains between r1 and r2, and r2 is greater than 1 and r1 is less than 1, right? Now notice that for all, so let me call this as boundary C1, the inside boundary, and the outside boundary as C2. So on C1 we see that r is less than 1, because on C1 r is r1 and r1 is less than 1, and we expect that from this equation we expect that r dot is less than 0. So all the arrows are, well, r dot, well, what have we got? So just a minute. I think it's easier for me to first consider the outer curve C2. We'll consider inner curve C1 a bit later. We'll come back to it, right? So we are going to come back to this C1, but on C2 we see that r is greater than 1. So when r is greater than 1, again this same equation, we see that r dot is less than 0, right? So r dot is less than 0 implies that we see that all the radial derivatives have a direction of arrow inward pointing. So which means that any trajectory which starts outside C2 is going to bound to come inside C2 because of the direction of the arrow. And similarly on C1 we can check that since r is less than 1, we have r dot is greater than 0 because again of the same equation, and now on C1 we have the arrows being pointing outward, right, in the positive r direction, which means that any trajectory which starts inside this this circle C1 is going to bound to go into this annulus region eventually. So which means that this annulus region is the so-called trapping region, is the trapping region of any trajectory. And what we have is that we expect that if there is a limit cycle, it is bound to stay in this trapping region. Why? Because any trajectory which starts outside this trapping region is bound to come into this trapping region, and that is a sure shot sign of having a limit cycle if it exists. Now the limit cycle will be, we can quickly check that the limit cycle is given by r equal to 1, because at r equal to 1 we have that r dot is 0, and that is where the trajectories neither increase or decrease radially. So the limit cycle is inside this trapping region given by r equal to 1. Okay. So that was an easy problem when we had to find a limit cycle, right? We can quickly also confirm that this particular case is not the case of a center. R equal to 1 is not the case of a center, but is the case of a limit cycle, because any trajectory will stay in on this curve r equal to 1, will never leave the region, right? So the region being the trapping region, right? So that is the pure property of limit cycles. Okay, so we have hit upon the limit cycle at r equal to 1.